In this slide, we will continue on example 4.3, and we will study the effect of step size on the approximation. And let's write the second part as examine how approximation behaves as h or step size changes. And we will use this, we will do this only for the m equals 4, the fourth order polynomial. That's why I will write f for m equals 4. You can try for higher or lower degrees as well, but it will have the same conclusion anyway. And our function for m equals 4 is x to the power 4. Let's keep this in mind, and let's start with writing the expansion, the Taylor expansion for, again, the first order. And for this case, we will have a slight change on the formulation to be able to make the h value, the step size, a parametric value so that we can play with it. And if you remember, the function was fxi plus 1, but instead of that, I will just write x plus h, because with I plus 1, we mean x plus h actually. If you remember, xi was 1 and xi plus 1 was 2. So difference is the step size. And that's why actually we can write this as x plus h. And we will predict this with the previous value, which is fx, and also the derivative, the first order derivative, fx times h. And the first order derivative, we can just find it from here. Fx is 4x cubed. And that's why we can just write here 4x cubed times h. So you can see this is now for the x plus h, we find we have a parametric function in terms of h. So we start with x equals 1. Then f1, the real value. By the way, let me write r1 here because we didn't put tilde on the left side. And f1 for the real exact function is 1. Then we can write this down as well, and let's truncate from the after the first term, and the prediction is 1 plus h equals fx is 1 plus 4 times 1 to the power 3 times h is 1. Sorry, h is h because it's parametric. We didn't change it yet. We want to change it and see the effect. It's just h, and when we truncate it after h here, so this is our prediction result, and simply it is 1 plus 4h. And let me write down r1 as well, and r1 is the remaining terms, which starts with the second order function derivative, and it is this divided by 2 factorial times h squared r2 f3 x 3 factorial h3 plus the other terms. And from here, if we calculate all the derivatives, for example, f2 x is 3 times 4, 12x squared. f3 x is 24x. f4x is just 24, and f5 is 0. The fifth derivative is 0, and the remaining derivatives are 0 as well here. So we will just use the first 4 terms here in the R1 calculation, and those becomes just R1. You can calculate them from the first term, 6h square, from the second term 4h cube, from the third term Ch04, and that's it. The rest is 0. So these are our this is our R1 function. And if we write everything down, for example, let's start with, so in this table you can see with different h values, step size values, we calculated the results. Let's start, for example, with 1, which gives us actually, if this is 1, this is 1, f2. So h is 1, then f1 plus 1, 2 is equivalent to 1 plus 4 times 1 is equivalent to 5. And R1 is, here we put 1, and R1 becomes 11. Similarly, here in the table we put 0.5, for example, h equals 0.5, then f is this time 1 plus 0.5, 1.5. So it predicts 1.5 equals 1 plus 4 times 0.5. It is 3, you can see. And R1 is, here we put 0.5, 0.5, 0.5. Then it becomes, for the 0.5 value, 2.0625. And we can calculate the exact values using this function here. And we can continue doing this. And you can see in the table we did this up to this value, very small step size. And you can see the exact results. And you can see the first order approximation. In the first one, step size is large. And in the last one, step size is too small. So we decrease the step size while going this way. You can see the exact value reduces. I mean, that's not important, but the important part is the difference between the exact and first order. You can see the difference is too large here, like 11. But when we decrease the step size, the difference in the approximation and the exact value is getting smaller and smaller and smaller, which shows or indicates that with the decrease of h, we can decrease the truncation error. So we can write it down here. If R1 decreases, then, not R1, but h. If h decreases, then truncation error decreases, which means accuracy increases. For example, with this very accurate value, we can still calculate f2, for instance, but we need to implement this for many values. So we will just have the exact value for just this, but we can add more and more and find the value of 2 again, and we can approach the function linearly, meaning that in the previous slide the function was like this for x, fx is x4, and with this very small step size over here, we will just approach very small increments, and all the small increments are linear, but it can capture the function easily because the error, you can see, is very small. So by increasing the h value, simply we will still approach to a higher order function with linear very small increments, and we can predict the results in a very accurate way. So it shows that there are two ways of improving accuracy. We can either, like here, we can just increase step size, increasing h step size, or the second one is we can increase the degree of the Tyler expansion. We already mentioned about it in previous applications. So this case was for only n equals 1 Tyler expansion, but if we use, for example, n equals 2, n equals 3, we will be able to reach this in a very accurate way with even a larger step size. Even if we use 1, for example, And if we use a fourth order Taylor expansion, we will get the exact results. Very accurate function with the Taylor expansion as well. So the second option is increasing Taylor series degree, or n, or adding terms to the Taylor expansion. So these are the two ways to improve the accuracy of the approximation with Taylor expansion.